We're now looking at a teaching video on coordinate geometry. Point 1, if we're looking at distance between point A and point B, we are looking at the distance, a straight line distance between A and B. So for a start, if a right angle triangle can be drawn, then the vertical distance, by the way, I have to rename this point C. The vertical distance would have to be the difference of the two y values of the points. So I have yb minus ya, and the horizontal distance, that is the distance between point A and point C, then I'm taking the difference of the two x values or the two x coordinates. In this case, I'll take xb minus xa. So other names given to the vertical distance: rise. Other name given for the horizontal distance: run. So if I'm looking for the distance between points A and B, the short of it is distance AB. And the formula, the distance formula we're using for AB would be I'll take this distance, xb minus xa, bracket squared, plus this distance, ya minus, I'll keep it in the same order, yb minus ya, bracket squared. So basically, how this formula is arrived at, we are basically using the Pythagoras theorem, taking ab squared equals to the square of BC plus the square of AC. So later on, to find AB, I take the square root of BC squared plus AC squared. Now there is also another variation to this equation. I could easily have just swapped this around. What I mean is this: xa minus xb. Here, ya minus yb. Now, so long as I'm consistent with the order of the x coordinates and the y coordinates. Now we look at point 2, gradient of the line passing through the points A and B. So the point here is point C, and what I take is the vertical distance, yb minus ya, and the horizontal distance, xb minus xa. So for gradient of the line AB, I can take it to be small m subscript AB. So that means gradient of line AB. I should just cancel this. Gradient of line AB. So the formula for this would be rise over run. This is rise, this is run. Another formula that is basically to replace the rise with YB minus YA divided by XB minus XA. I can also have YA minus YB divided by XA minus XB. Now we look at point 3, midpoint between point A and point B. So if we are talking about midpoint, then the point in between is labeled as big M, point big M. Now the ratio for AM is to MB would be 1:1. So the midpoint between points A and B would be the average of the x values or x coordinates, comma, the average of the y coordinates. So that is if the point in question is the midpoint, big M, and the ratio AM is to MB is 1:1. Now we look at ratio theorem, point 4. There are two cases here. Case 1, internal point of division. In other words, if I'm given A and B, so I have to find a point that is in between A and B. So say point C that I have to find right now. But the ratio of AC is to CB is not 1:1. So AC is to CB is not 1:1. So if that is the case, then there must be a way to cope with it. So the coordinates of C will be, now I will take this M multiply to the x coordinates of B. So M XB plus this n multiply to the x coordinates of A. So n XA over, they are all together m plus n parts. So look at it carefully. I'm going to run through the same process for the coordinates of y. So I will take this m, which is on the other side of the C as B. So I take the m, multiply to YB plus n multiply to YA divided by n plus n parts. So this is internal point of division. For the second point, we're talking about external points of division. And if A and B are given, and we need to find C, and C is outside of the length AB, then this is what will happen. To find the coordinates of C, I will have M multiplied to the x coordinates of B minus N multiplied to the x coordinates of A. Then, for the divisor, I will have M minus N. Next, to consider the y coordinates of C, I have the M multiplied to the y coordinates of B minus N multiplied to the y coordinates of A divided by M minus N. Now, if you can remember this, then that is good. You can apply the formula straight away. But in the event that we forget, we have another way to do it. That is, to work out what this is, which is M minus N. So the way to do this is to take this point, point B, equals to, I will have M minus N times XC plus N times XA over, well, the whole part from A to C, we have M. Then, follow the same thing, just replacing the x with y. M minus N times YC plus N times YA over N. Now you can see this is basically what we had in part A. But for this case, external point of division, then there is a direct formula to go about it. Now for point 5, we'll look at collinear points. So for collinear points, A, B, and C, what we mean by that is this. Point A, C, and B are on the same straight line. But the relationship between the gradients of the line segments AC, AB, and CB would be, for part 1, the gradient of AC is the same as gradient of AB, is the same as gradient of CB. In other words, if we are considering a straight line, any point on that straight line will have the same gradient. Similarly, if you are looking at line segments, whether it's AC or AB or CB, all line segments will also have the same gradient. Next, for part 2, if I'm looking for area of a triangle, in this case, triangle A, B, and C, you realize it's just a line. then the area must be a 0. So one way to test whether the 3 points are actually collinear, we can actually use this. Are the gradients between the line segments the same? Or another way to test it would be, try to find the area of the triangle ABC, whether the area is 0 or not. If the area is 0, then we have a case that A, C, and B are collinears. Now for point 6, we look at parallel and perpendicular lines. So if the two lines are L1 and L2 and their gradients M1 and M2, then when L1 and L2 are parallel, then the M1 is equals to M2 if the two lines are parallel, then their corresponding gradients must equal. So if the two lines are perpendicular to each other, then the product of the two gradients must be -1. So when I'm talking about parallel lines, it's two lines arranged in such a way that they do not meet when I extend the line indefinitely. Or another way to think of it is that the perpendicular distance between the two lines are always the same. As for part 2, perpendicular lines, the two lines are at right angle to each other. So the product of the gradient would be -1. For point 7, we look at equations of a straight line. Now I put down there equations of a straight line because there can be many forms that I can present. So for point 1, gradient form, you will have y equals mx plus c, where m is the gradient of the line. And gradient simply means the measure of the steepness of the slope. And c is just the y-intercept. And this is the point where the straight line cuts the y-axis. Then for part 2, we look at the intercept form. We have x over a plus y over b equals to 0 or equals to c. So the a here is basically the x-intercept. That is where the line cuts on the x-axis. And for this, the b is actually the y-intercept, where the straight line cuts on the vertical axis, the y-axis. For the general form, it will look like this. ax plus b y plus c equals to 0. So we have three forms, and we can choose to present the equation in any of these forms. But also, when we are given any of these forms, we should be able to extract the relevant information, the gradient as well as the intercepts, whether it's the y-intercept or the x-intercept. Also, another way to use it is, if we're given this form, how we can quickly sketch the straight line on the Cartesian plane. Now, for point B, formally for forming straight line equations, there are two cases. The first one, given only the gradient and a point. So the arrangement could be this. A point here on a straight line. The coordinates is x1, y1. And the gradient of the line is just m. So in situation like that, and I have to find the equation of a straight line, I'll make use of y equals mx plus c. So what I'll do is to replace this m with the value here, and later on to find the value of c, I will substitute the x1 into the x here, the y1 into the y, in order to find the value of c. And after that, I will have a complete straight line equation. Alternatively, I will have this formula, y minus y1 equals to gradient times x minus x1. To use this formula, I must not substitute any value of the y and any value of the x into the y and x here. And the place for substitution is indicated by x1, y1. So what I'll do, take this value, put it in here, take that value, put in there. And this m is replaced by the value here. After rearrangement, the straight line equation will look like this, y equals mx plus c. And the next one, if on a straight line I'm given 2 points, one is the x1, y1, the other one x2, y2. If these 2 points are on a straight line, and that's the straight line I'm trying to find, then the formula I can use is this, y minus y1 over x minus x1 equals to y2 minus y1 divided by x2 minus x1. So this has an advantage over the other two formulae. If I chose to use this, then first of all, I have to work out the gradient from these 2 points. Then, with the gradient in, I use any of these points, the information of the x and the y coordinates to work out the c. You can see then the working is not top down, it's broken up. There isn't a constant flow. For this formula, all I need to do is to put into the x1 and y1 the information of this point, x2 and y2 the information of this second point here. Then I'll work through from top down to the final equation of a straight line. So the working is not broken up. So the advantage is, if we are given 2 points, then use this formula, given a gradient and a point, any of these two. Point 8, we are looking at the area of polygons. So when we talk about polygons, we are basically saying straight sided figures. So we can have triangles. That is the smallest number of sides we can have for polygon. And we can have quadrilateral, 4-sided. And then we can have the 5-sided pentagon, 6-sided hexagon, 7-sided heptagon, and so on. So basically, this formula is so versatile, and no matter how many points or vertices of that straight-sided figure you have, we can just work out the area. But a word of caution, the way we take the points must be in a cyclic manner. And it must be anti-clockwise. Now, let's look at part 1, for instance. If I have a certain figure there are many other sides. So the first point, point A, XA, YA, then point B, XB, YB, and I have C, XC, YC, and so on and so forth. Now, the way to find the area of the polygon would be I will take half of. Now, let's begin with this point, and we take points in cyclic manner and also in anti-clockwise direction. So, XA over YA. Then XB, YB, XC, YC, then XM, YM, XN, YN, and I must close the cycle with the starting point XA, YA. So to work it out, it would be, now sometimes this method is called the shoelace method for a reason. The reason is simple. It goes this way. It's like tying your shoelaces. And then this way. So we do it this way first. XA times YB plus XB times YC and more. Then XM times YN plus XN times YA minus I will go from bottom up, the YA times XB plus the YB times the XC. Then the YM times XN plus the YN times the XA. So this will actually produce the area of the polygon. But the K must be taken to take vertices of the coordinates, the vertices of the polygon in cyclic manner as well as in anticlockwise direction. Supposing that I just want to focus on the triangle ABC, then it will be just looking at this. Then the area of triangle ABC would be half. I'll take XA, YA, XB, YB, XC, YC, then back to the original point XA, YA. Then to extend it, half XA times YB plus XB times YC plus XC times YA minus, I'll go bottom up, YA XB plus YB XC plus YC times XA. So it really doesn't matter how many points we have on the vertices of how many points of vertices the polygons have. We can actually work out the area of the polygon using this formula. So we have looked at many things, but all these are the formula. I have just given you some understanding how the formula works and how to best apply in different situations. So this is basically what the video is about.